Hello, everybody, and thank you for joining today's Health Effects Institute webinar. My name is Chloe Danforth, and I'm a senior scientist here at HEI. Let's see if I can make my screen advance. Before I turn this over to our moderator and start delving into the webinar, I'd like to make a few housekeeping announcements. All attendees will be muted for the duration of the webinar. You can turn on closed captioning at the bottom of the screen to the right of the Q&A button. We will have a very little time between presentations for 1 or 2 questions, but we will reserve about 20 minutes at the end for a more extensive Q&A discussion period. So if you have any questions, please submit them via the Q&A function at any time during the webinar, and you can also upvote questions in that same Q&A box if you agree with or have the same question that's being asked. If you experience any logistical difficulties, please contact us through the Q&A box. We will be monitoring that through the webinar. So just a little bit about us before we get into it. HEI is a nonprofit corporation that was chartered in 1980 as an independent research organization that provides impartial science to inform decisions that foster a healthier environment and better health for all. And since 2022, HEI's energy research program has supported research to improve our understanding of potential population exposures associated with unconventional oil and gas development in the United States. We have currently a number of studies that are wrapping up or are underway that seek to understand potential population exposures to air emissions, noise, and changes in water quality from oil and gas operations in different regions across the United States. And there are some that are also examining trends in air quality, so how changes in oil and gas operations and governance might explain any trends in those air emissions, among other factors. So before I turn things over, I would love to acknowledge my co-organizers at HEI and thank our speakers and moderator for joining us. So now I am very happy to introduce our moderator, Dr. Ted Russell, and one of our speakers. Dr. Russell is the Howard T. Tellefson Chair and Regents Professor at the Georgia Institute of Technology in the School of Civil and Environmental Engineering. His research interests include air pollution modeling, aerosol dynamics, atmospheric chemistry, and combustion emissions control. Dr. Russell is a fellow of the American Society of Mechanical Engineering and the American Society for the Advancement of Science, and is a National Associate of the National Academies. He was a member of the Environmental Protection Agency's Clean Air Science Advisory Committee and a member of the National Research Council's Board on Environmental Studies and Toxicology. Ted has also been a member of the HEI Energy Research Committee since its inception in 2017. On that, I'll let you take it away, Ted.
Thanks, Chloe. And as Chloe said, I'm Ted Russell, and I'm both a professor at Georgia Tech and also a member of the HEI Energy Research Committee. And what I wanted to do is, just before we get started, is to give you an idea of how we got to this place and, you know, the whole TRACER collaboration. And what really led to this is the HEI Energy Research Committee did an extensive review of the literature on assessing potential exposures and the health effects of UOGD activities. And what we found from this review is there was a need for better exposure quantification. So while a great deal of scientific literature reports on air quality near such developments, the source-specific contaminants and their link to specific processes is less well understood. So what the research committee did is, along with HEI staff, is develop a call for proposals, provide tools and measurements to improve classification of exposure. We got a lot of great proposals coming in, and we had to choose 3. And so you're going to be hearing from those researchers. What we did, somewhat unusually, is that the committee members worked very closely with the research teams to tailor the projects to best meet the overall needs of the program and to look at specific oil and gas development processes and how they link to long-term exposures. And through that, we developed this collaboration between the teams, which I think has worked wonderfully. And I think the seminars you're going to see today really show to that. And this collaboration involves air quality modeling, monitoring, and linking these two. The outcome, as designed, was this TRACER model is a central focus of the work. And the model does is it can predict chemical emissions, speciated chemical emissions, and their effect on air quality. understanding this linkage is important for determining science-based setback distances that separate operations from sensitive land uses, such as homes and schools, and how the emissions from oil and gas operations might link to regional air quality and contaminants like ozone and particulate matter. The model can be adapted for anywhere in the United States and be able to help us understand as the emissions from oil and gas operations change over time. And with that change, the TRACER model can be modified to account for those, how that links to potential exposures. Initially, the model was developed and evaluated for use in the Denver-Julesburg region of Colorado, the Eagle Ford Shale region of Texas, the Marcellus region, which intersects parts of Ohio, Pennsylvania, and West Virginia. In conjunction with the model development, the teams monitored air quality and noise to improve this understanding and these linkages and the quantification of potential short and long-term human exposures in Colorado, New Mexico, and Texas. In addition to understanding the exposure in these locations, the air quality data are useful for evaluating and refining the TRACER model and other models as well. You will also be hearing about a special program that comes out of NASA's funding. It's NASA's Health and Air Quality Applied Science team. And I'll talk a little bit more about that and how it links to the TRACER project as the fourth talk, with really the outcome to improve our understanding of the products of transformations and the larger overall footprint. But another thing is just to really show how satellite data can be used for understanding the impacts of UOGD operations. So with that, what I'd like to do is introduce our first speaker, and we hope you enjoy this event. So with that, I would like to pass it off to Dr. Leah Hildebrandt Ruiz, who is an associate professor in the Makeda Department of Chemical Engineering at the University of Texas at Austin. Her research focuses on the formation of air pollutants, their transformation and atmospheric fate, make better informed recommendations for environmental policies aimed at improving air quality and human health. Her team uses a combination of state-of-the-science instrumentation in laboratory experiments and to make field measurements in indoor and outdoor environments, as well as mathematical modeling. With that, Leah.
Thanks so much, Ted, for the introduction. So yeah, I'm going to be talking about our project, which was based out of UT Austin. And we spent a lot of time and effort to work on this model that Ted just introduced, and also took measurements to evaluate the model as well as to provide input information to the model. So as you may know, there is 2 webinars. This one today is focused on measurements, and that's what I'll focus on in my presentation, but we'll talk much more about modeling next time. And I'm here with my colleague, Paul Mushtel, who will talk about some of the measurements. So we are, most of our team is based out of UT Austin. These are just the PIs and co-PIs, the pictures of the PIs and co-PIs from UT Austin. And then Dr. Lucas Henneman is from George Mason University, with different expertise really coming together to work on these measurements and modeling. And then a big group of postdocs and graduate students and research scientists that have been working on this as well. And so really our whole study was motivated by developing this TRACER model that Ted just introduced. And really what we did is we had already, my colleague, Professor Dr. Allen, had already developed a model that allowed us to model the emissions and dispersion of methane. And so what we did is to take that model and expand it to other pollutants and other sources of pollutant. So the TRACER model is really a coupled emissions and dispersion model, but we can also couple it to chemical transport models. And then we did targeted field measurements to evaluate, refine the model, and provide input to the model, as well as exposure analyses. Our project was mostly focused on the Eagle Ford Shale, but was then also expanded to include measurements in the Permian, which we'll talk about today, and then also modeling in the Marcellus Shale. And so this is kind of an overview. I've kind of split our project tasks into these 7, and we'll focus on tasks 1 and 2 today, but then talk about the other tasks and the modeling webinar. So I'll start talking about measurements that we took in the Eagle Ford Shale, and just in general, we have a stationary and mobile measurement platforms. Stationary meaning this is a movable trailer that we can tow to a particular location, instrument it, and then take measurements for a certain period of time. And we have an electric van that we also instrument and drive around. And this really allows us, the van allows us to give a greater spatial coverage, but not all instruments are happy being moved around all the time. So that's why we need the stationary trailer as well. So again, starting with measurements in the Eagle Ford Shale, we used our mobile platform mostly for movable measurements. So we collect measurements while we drive around, and then when we see a plume, we temporarily park our van next to that plume to take measurements. And again, we can do that because it's a fully electric vehicle, so we don't have to worry about measuring our own pollutants. And so these are 2 campaigns that we conducted in spring and fall of 2023, and the black dots kind of indicate the sources we sampled. So when we focused on flaring emissions during these campaigns. So for most of these, we were parked next to a flare, measuring the plumes from these flares. It's more like a nicer picture of what the data look like driving around. And so what you see here is the background is a satellite image of the area in and around Karnes City, which is in the middle of the Eagle Ford Shale. What you can see on the satellite image all of these different rectangles, which are the well pads in the area. So this is an area of quite dense oil and gas production. And there's dry gas, wet gas, as well as oil production in the region. And so here we are driving around in this region. And what I'm plotting on this graph is benzene, toluene, the concentrations of BTEX, basically benzene, toluene, and C8 aromatics. So our instrument cannot distinguish between silenes and ethyl benzene. So they are added together for this plot. And what you can see is that we're driving around, and when we're driving near sources, for example, some of these flares, we see a clear enhancement of those concentrations. And this is just an image through the dash cam as we approach one of the flaring sites. We did not work with operators for this study, so all of our measurements were taken from public roads. So when we are close to a flare, there is, of course, the possibility that our emissions are influenced by non-flaring emissions. And so what we did to separate the influence of flares and other sources is to conduct source apportionment analysis. And this is an example of the result from such an analysis, where we basically come up with different factors. One of them is a flaring factor, which is kind of characterized by having methane, hydrocarbon, and CO2 emissions versus more evaporative emissions, which have the methane and the VOC emissions, but not the CO2. So with this source apportionment analysis, we can distinguish the flaring from the non-flaring emissions, and then calculate destruction efficiencies and emission factors for the flares. We also took measurements at our stationary site, and that allows us to get kind of nice time series and look at trends over time. In this plot, we are plotting the methane concentrations, which are plotted on the left vertical axis in blue, and then concentrations of some alkanes plotted on the right vertical axis. And these are from GCs and then a Picaro methane instrument. And what we can see here is periodic enhancement at this site. This stationary measurement site is in the middle of the Eagle Ford Shale, but not adjacent to a particular well pad. So we see periodic enhancements of methane as well as hydrocarbon concentrations. And one thing that was interesting and that I want to point out here is that these peaks all occur in the early morning, kind of 3 to 6 a.m. is when we see the peaks, when we see them, right? We don't see the peaks on all days. So we did quite detailed analysis of the data as well as of modeling activity to try to understand whether there is some non-routine emissions occurring in the early morning hours, or how much of these peaks could be explained by meteorology. And we'll talk about that more later, but I wanted to point out first sort of the phenomenon of having the higher concentrations. And I'll give you a little bit preview, which is that many of these peaks can indeed be explained by routine emissions, so really emissions that occur similarly every day, combined with favorable meteorology, which in this case is lower boundary layer height at night, which that occurs every night, but also low wind speeds, actually, really resulting in this pretty high peaks at this background site. We also measure particulate matter and particulate matter composition at the stationary site. These are data from fall of 2023. And broadly, what we observed are fairly high concentrations for what would otherwise be a background site. So we see fairly high PM concentrations at this site, also great variability in concentrations. This is green is organic aerosol, red is sulfate, blue is nitrate, and orange is ammonium. And something you can't see directly here, but that we are able to see with further analysis is that concentrations of particulate matter were higher when the air was coming from the north-northeast direction, which is a direction where you have higher well density, as well as a predominant oil production as opposed to gas production, which is to the south of the site. So this is quite just a quick preview of the data from the Eagle Ford Shale, and I'll turn it over to my colleague, Paul Mischel, to talk about some of our measurements in the Permian Basin.
Thanks so much, Leah, and hi, everyone. My name is Pavel Mischel. I'm an assistant professor at UT Austin, and I had a pleasure to be a co-PI on this HAI project. And you just heard from Leah about the measurements in Eagle Ford Shale, and we were like wondering how cool it would be to actually go a little bit further to the Permian and do some measurements there. So thanks to HAI, we are very grateful it was possible, and some other HAI grantees already have been doing some continuous measurements there. So it was a interesting campaign because we needed to go far away. The van has a relatively short range, so we needed to go all the way. But it was exciting because we had several different anchor points: Pecos, Odessa, Midland, Loving, Carlsbad, Artesia. And this map just shows methane mixing ratios, because we did, we basically, the goal was to try to fingerprint and understand spatial extent of the impacts from oil and gas. And one of the exciting opportunity was actually to collaborate with the team, Meredith Franklin's team in Loving. And here you can see both mixing ratios for methane and for benzene. They are spatially correlated. You can see sometimes the hotspots exceed of mixing ratios of methane exceed 4 ppm even. And benzene can also be, we saw some record concentrations close to the source directly from the flue. And next slide. And just to basically visualize as an example that we can go to one of the sources, we saw some also unexpected sources, and we basically parked and we were able to fingerprint those sources. So here on the left, bottom left-hand side, you can see there is a fingerprint of one of these emissions. You can see homologous series of aromatics spanning from C6 to, can even see more than C14, and some oxygenated compounds as well. And next slide. And what was also interesting is that we were able to do some stationary measurement, just collocated for a couple of days in collaboration with Meredith Franklin's team. And as you can see, like, because they have continuous measurements of certain compounds, we are just showing here collocation for benzene and toluene. And we didn't expect excellent agreement because the inlets were in slightly different places and so on, but it was actually pretty amazing agreement. So really good agreement. Next slide. And basically, we were able to look at other correlational analysis, and also you saw some factor analysis that we conducted. And each time the wind was blowing from those sources, on the right-hand side, you can see the Google Earth imagery. So all these little squares are actually all oil and gas extraction activities, and basically you can smell like those more sulfuric and you can see there's like H2S and lots of other markers go up, but we measured a lot more than that. And because of the short time, well, I will turn it over now to Leah, but thank you.
Thanks, Paul. And so, yes, just a couple of key findings from our measurements, again, trying to summarize kind of, months and months of data. But we did observe high diurnal variability of VOCs, which would translate into high variability of exposures with highest concentrations at night and the early morning. Sometimes those are due to routine emissions and favorable meteorology, and sometimes they're due to non-routine emission events. The emission factors and destruction efficiencies from the flares are variable, and we can get to those data through factor analysis to separate the influence of other sources. And then we do see differences in emissions and concentrations in the Permian compared to the Eagle Ford Shale. One of the main differences are higher concentrations of sulfur-containing compounds. And with that, that's our quick overview, and I'll turn it back over to Ted. Thank you.
Thanks, Leah and Paul. Hopefully you all can hear me. Wonderful, really exciting stuff. What I'd like to do is move to our second speaker and introduce Dr. Meredith Franklin, who is an associate professor in the Department of Statistical Sciences and the School of the Environment at the University of Toronto. Her research there focused on the development of spatial temporal data and analysis methods in statistics and machine learning for environmental data analysis, with a primary interest in quantifying environmental exposures and their impacts on human health outcomes. And with that, Meredith.
Sorry, I realized I hadn't unmuted myself here. There we go. All right, thank you for the nice introduction, Ted. So yes, our project is on assessing source contributions to air quality and noise in unconventional oil shale plays. And to follow the theme of this webinar, I'll be speaking about our measurements from our project.
Hey, Meredith, you are on the wrong screen. You have to switch to the other presentation screen.
Okay. Is that better? I swap the displays? No?
We still see the thing on the side.
Let me try again.
Yeah, great.
Better.
Oops.
Nope.
Okay, let me try once more swapping it.
Yeah, perfect.
Got it? Awesome. Thank you. Okay, so study motivation. Some of our work here on the right from our earlier work looking at flaring in particular, from satellite observations, we saw the density of gas flaring in the Eagle Ford Shale and the Permian Basin really reflecting increasing oil exploration. And then, as you can see from the plot on the left, that annual oil production has increased over 8-fold since 2010 at wells located in the Permian Basin. So to describe our measurements, I'll talk about two types of measurements that we did. The first is that our aim was to characterize the impact of unconventional oil and gas development activities on ambient air pollution, noise, and radioactivity by collecting high temporal resolution data from a stationary monitoring platform that Powell showed a little bit of, where his mobile measurements were taken around this stationary platform. This stationary platform was located in the Permian Basin on the New Mexico side in Eddy County, New Mexico, as you can see here on the map, and specifically located at the ConocoPhillips field office in Loving, New Mexico. This is the picture of our trailer, and then here on the right is the picture of the inside of our trailer, all the instrumentation. And so our approach here was through a combination of automated, continuous stationary atmospheric monitoring and source apportionment modeling. Our aim is to identify the UOGD processes that result in higher ambient air pollutants, radioactivity, and noise. And so we conducted these measurements in conjunction with another set of measurements. And so our second set of measurements were to deploy passive sampling. And so for this intention was to really understand the spatial distributions of targeted petroleum hydrocarbons in the ambient air. So again, we deployed a spatially dense set of passive samplers around the trailer in Eddy County, New Mexico, in the Permian Basin, also co-locating one with our trailer. And so that was done at the time of our stationary platform measurements, and then more recently moved to Karnes County, Texas, where Leah's team was working, and we deployed some passive samplers there. In the Loving, Carlsbad, New Mexico area, this is a zoom in for that, we had 7 samplers, including the one co-located at our trailer. And then in Karnes, we had 4 samplers. What we measured, so the main sampling period of the trailer was from May 1st, 2023 through the end of May 2024. And at that site, we measured all sorts of things. As you can see from the inside of the trailer, there was lots of instruments. We measured air pollutants, greenhouse gases, and radioactivity. The ones that I'll be focusing on today to show the results of are highlighted in blue. So methane, VOCs, nitrogen oxides, ozone, and radioactivity. We also measured noise. And then the passive samplers, which were matching this period of time in the Permian Basin, but then, as I mentioned, moved to the Eagle Ford at a different time. There we were measuring C6 to C10 hydrocarbons. And as you can see here, this is on the right, a picture of just the density of the wells in the area around where the trailer was located at this blue marker. And then the red is showing the flares also nearby. And as you can see from the actual picture, this is a double flare that was located up here closer to Carlsbad. So part of our purpose here was to do these measurements and also compare our results to work that our team member Detlev Helmig has been collecting at the same time in the Colorado Front Range. So I'm just presenting this slide as a comparison because many of our results will be comparing to concentrations in the Denver-Julesburg Basin. And this is just show the 5 sites that we often are comparing our concentrations to. And they were operated by Boulder Air and use the same exact measurement techniques that we had at our Loving, New Mexico site. And this is just to show you the distribution, spatial distribution of those sites. Oh, I'm sorry. And where the main oil and gas production area was up here, and then the distribution of the sites was down here, indicating basically what we're comparing to. So just to go through some of the results of the data measurements and the analysis that we've done on these data, we can see to start off with, we'll focus on methane. We can see at methane that we see high concentrations of methane compared to the DGB sites. And we have that Loving is really a much more central site to the oil field. And that we can see that the higher concentrations of methane there. If we zoom in now to methane at this site in terms of looking at the time series over the time that we measured, we show frequent high concentration plumes. We also see seasonal changes with higher concentrations in winter due to reduced atmospheric mixing and less sunlight. We see the yellow line here is the running mean, but we see how much variability it is showing at our site in methane. And then we also show here the background site of 1.92 ppm and our measurements compared to that. Now, again, if we look a little bit closer at the methane, we see plumes at all directions, and directions are down here and then at all daytimes. So, and again, just to describe the box plot, we see the general distribution from the 5th to the 95th. So basically the lower bound and upper bound, the median will be the line in the middle, and then the outliers, which is why I'm pointing this out, because this is basically showing the depiction of the methane plumes above the 95% line. And we see that those are occurring at all times of the day. We do see the median levels are higher at night. about 50% above the background. And then in terms of direction, we see the levels from the southeast all the way to the southwest are higher, 25% higher. And this really highlights the fetch of the air over the Permian-Delaware Basin coming to our site, which is at the sort of the western edge of the Permian Basin. Moving on to ethane. Again, we see ethane at Loving, New Mexico compared to the Colorado sites is quite a bit more elevated. And then as well as benzene. So we also see higher concentrations of benzene that were on average about 9 to 11 times higher than those in the Colorado comparison sites. And I'm mentioning these, highlighting these because really the driving force behind ozone formation, which is another component that we want to really focus on from our measurements, that we see that measured hydrocarbon reactivity is really driving ozone formation. And we see from our measurements that the largest contributor to the regional photochemical ozone formation is really the petroleum hydrocarbons. And combined, the hydrocarbons associated with oil and gas production can contribute here to more than 90% of the measured total ozone formation potential. And so this is work that we've shown here with these data that also confirms prior findings that have been recently published by some of our colleagues, basically saying that hydrocarbon emissions from oil and gas exploration, particularly the alkanes, which are shown here in pink, dominate the atmospheric reactivity and thus the ozone formation potential. And so we just wanted to highlight that. Another thing that is driving ozone is the nitrogen oxides. Now, we don't have as many measurement comparison sites in the Denver-Julesburg, but we do see that Loving does have higher concentrations. And then when we look at our nitrogen oxide concentrations with respect to wind direction, we see sort of peaks from different sources. So of course, nitrogen oxides are sourced from traffic and, urban activity. So we see, sort of a little bit of a hump here from the city of Loving. We also see a peak from flaring in the northwest, closer to Carlsbad, where that double flare that I showed before is located. And we also had a well pad right next to our trailer. And so we're seeing a peak there as well. So all of these sort of precursors are to show our results of ozone. So ozone, just as a refresher, is high during the daytime primarily. It's a photochemical pollutant, so especially from noon to 6 p.m. and under clear skies. And we see that it's higher in spring and on summer days from April to October. It's higher when it's dry, the humidity is low, and when temperatures are high, and when winds are weak. And when, in our case, the air is moving slowly from out of southerly or southeasterly directions. And just as in a historical context, typically since 2018, the Southeast New Mexico has been seeing exceedances of the 70 ppb threshold. So the 70 ppb is the National Ambient Air Quality Standard for ozone, about 20 to 30 days each year. And for calculating the NACs, that's the fourth highest daily 8-hour maximum that enters the legal limit calculations. So specifically from our site, we see on the left is our 1-minute data, because we did collect data at the 1-minute time resolution. But then when we take the 8-hour average data to match how the regulatory standard is set, we did find during our study period that 39 days were above the 70 ppb NACs. And so that's, again, May 23 through May 2024. So it included basically one summer. Also comparing our Loving site's ozone to the Carlsbad NMED site, there's a state site closer to Carlsbad, the city of Carlsbad on the outskirts. And we do see that the NMED data from the state's monitoring location is tracking very similarly with our measurements. We remember that ozone is a regional pollutant, so they're tracking very closely. They're about 11 miles apart. So that is just showing, the sort of the wider reach of the ozone concentrations, and that we are seeing that not only at our site, but that it's happening at the site that's closer to Carlsbad. Okay, now in terms of radioactivity, so hydraulic fracturing can mobilize radioactivity. There's been a few studies on that recently, and so we were interested in taking a look at the radioactivity. So radioactivity through the hydraulic fracturing can occur by sort of stirring up the soil where there's a radioactivity material, and then it can be emitted, and we can detect concentrations from that. So we wanted to show some of our results from the radioactivity. This is a novel measurement that we made at our site. So we calculated total radio. So we measured radon gas and particle radioactivity, and the results I'm showing are for the total of that, so total radiation. What we see from our measurements is that total radiation is approximately 2 times above the typical background levels. We also see the diurnal patterns where the radiation builds up at night, and it's 2 to 3 times higher during early morning hours. And we're just showing some levels here. That this orange line is depicting the EPA lower action level for indoor air. And then this gray shaded area is the continental background. So that's where we're showing the sort of the higher than background levels. And then we also see some spatial trends in this, that it's highest during low to moderate northwest to northeast winds, and that winter values were more variable and approximately 2 times higher than in summer. And then finally, for radioactivity, we also did some analysis with the high split model, and we found that the probability of total radioactivity at the Loving site, this is showing the probability greater than the 50th percentile, and we just see the spatial distribution of that, where the strongest surface source of the area basically overlays with the city of Carlsbad to the northwest, and then the sector to the southeast of where all the drilling is occurring. And then the other thing we wanted to highlight was how the radioactivity correlates with our hydrocarbon measurements. We see with methane, the correlation, or the R squared in this case, was about 0.5 with the scatter plot here between these two. And then as well as benzene, we see, again, a moderate correlation. Now, moving on to our passive sampling, spatial distributions. The intent here was to really understand the spatial distribution of the hydrocarbons. So we see these dots are from the 7 sites that we had deployed. And we're just, again, referencing here, the orange dot shown down here is actually the co-location with our trailer. These are methocyclohexane concentrations, and which is one of the tracers that we measured from the passive sampling. That's a typical oil production related hydrocarbon. We see the strong gradients that correlate spatially with the well density. And so as you can see, the well density is obviously increasing here south of the Carlsbad area, which is up here. And we see the concentration similarly following that spatial trend. From this passive sampling, we can also get some temporal trends. And again, we're doing a few comparisons here. We do see, so this is showing both the Permian Basin on the left, so the seasonal changes of benzene abundances across the Permian Basin, which we see a strong seasonal trend. And then this is very recent data that we just finished from the Eagle Ford, where we're seeing that lower benzene abundances across the Eagle Ford. And while we don't have as long of a time series of collection in the Eagle Ford, we don't see such a strong temporal pattern as well. And then here again, not so as clear to see as I can see on my screen here, but this is a comparison. This is our trailer benzene. This is the sampling network benzene concentrations. And so we see that the trailer has a lot more variability. Obviously, we have a lot more data here, so it's picking up peaks from that. And the network is tracking, in terms of the median. And then we do see that comparisons with other sites in Texas, Odessa, Houston, Dallas, and San Antonio. And so we do see that the concentrations that we measured both through the passive sampling and through our trailer were higher than the than the other sites located in Texas.
And Meredith, we're just about at time.
Okay,
wonderful.
Summary 1 and summary 2, and then I'm done. So summary 1 is just to quickly summarize what we found from the trailer. We implemented the continuous air sampling from May, April 2023, operated for 1 year. Compared to the Colorado sites, the levels of methane, non-methane hydrocarbons, as well as ozone, nitrogen oxides are significantly higher. The oil and gas development completely dominated the methane emissions in the area, with all those plumes that we were seeing that are a good indicator for industry-related pollutant emissions. Eddy County, New Mexico has been exceeding the ozone NAAQS Comparing our data with other prior monitoring results suggests that ozone pollutants levels are decreasing overall, but that's in our location, the trends are defying what is seen in the rest of the country. Our data and several other prior peer-reviewed studies suggest that regional ozone is largely due to significant VOC emissions that we also measured and saw from oil and gas operations. And then finally, in summary, for the passive monitoring that we did, we had those 7 sites in the Permian and 4 in the Eagle Ford Shale. We captured spatial gradients of the hydrocarbons. We saw clear gradients in oil production from the hydrocarbon markers, as well as benzene, where well pad density is higher, particularly in the Permian Basin. The seasonal changes in all hydrocarbons were observed, particularly in the Permian Basin. And concentrations on average were higher in the Permian Basin than in the Eagle Ford Shale, and as well as higher compared to the Texas sites, as well as the Colorado sites. And overall, to the best of our knowledge, in overall summary, that this has been the most extensive air monitoring program in the Permian Basin in particular, both with our passive sampling and our trailer measurements, and our measurements in the Eagle Ford Shale have complemented prior work in this area. So with that, I thank you very much. And this is our team. And yeah, I'll pass it back to you, Ted. Thank you.
Thanks so much, Meredith. And I'd like to introduce our third speaker, who is Dr. Jeff Collette. He's a university distinguished professor in the Department of Atmospheric Sciences at Colorado State University. Dr. Collette's group has conducted field studies of air quality and atmospheric chemistry at more than 40 locations across the globe. His research interests include pollutant processing by clouds and fogs, nitrogen deposition, air quality impacts from unconventional oil and gas development, and regional air quality, among others. So with that, Jeff.
Thank you, Ted. I'm pleased to have the opportunity to join the webinar to talk about some of the key findings from our HEI energy-sponsored work looking at concentration increases of air toxics and other pollutants near oil and gas well drilling, completion, and early production operations. I'd like to acknowledge my co-authors on this air monitoring part of our study from Colorado State University and the Colorado School of Public Health, and also our colleagues at the state of Colorado who deployed mobile monitoring assets around the well pads we were studied and contributed significantly to the data sets that were generated. So I think everybody on this call, oops, sorry, I'm not getting the slide to advance here. Well, there's always something that goes wrong. Usually it's not the slide advance. Let me try resharing. All right. So everybody on the call, I think, is aware that improvements in directional drilling and hydraulic fracturing technologies have allowed the U.S. to become the largest producer of both oil and natural gas. And we're going to focus today on one of the basins that's responsible for part of this production increase, and that's the Denver-Julesburg Basin. So in our study, we're really interested in looking at emissions and air quality impacts associated with specific operations. And we're focused primarily on pre-production into early production. So for example, if you look at this aerial view here, you can see one well pad undergoing drilling operations, another undergoing fracking operations, and there is very different types of equipment there. There's also a significant difference in terms of the contact between the subsurface hydrocarbon deposit and the atmosphere in these different stages. So for example, during drilling operations, we might have emissions from diesel or natural gas powered drilling rigs, along with the material that's coming up from the subsurface that includes drilling muds used to lubricate the drill bit, to move drill cuttings, to the surface, as well as entrained hydrocarbons from that subsurface deposit. If you go to a stage like fracking, things are a little bit different. Their material is primarily being pushed down well, so we don't expect to see a lot of subsurface emissions during that stage. However, there's a lot of power generation on the surface. In the well pads we studied in this particular investigation, they were using grid-powered electrified drill rigs, removing that sort of combustion signature at the surface. But during fracking, there's a lot more power required, and so we tend to see more of a combustion signature. And then there are other stages as well, including flowback, when injected water and produced water from the formation come to the surface and can be handled in different ways. In work that we published in 2019, we demonstrated that the largest emissions of benzene and many VOCs were associated with flowback operations. But also, as I'll show you in this study, the implementation of newer closed-loop tankless systems for fluid handling have greatly reduced some of those emissions during flowback. So before I get into talking about results, just a little bit about our air monitoring approach. So we studied 3 sites across the DJ Basin. These included 4 different well pads undergoing pre-production into early production operations. And these were operated by 3 of the major oil and gas operators in the DJ Basin. Our colleagues at the state deployed their mobile monitoring lab, which had onboard speciated volatile organic compounds, or VOCs, methane, NOx, and fine particles. We deployed weekly integrated canisters around the pad and at a background site, typically a couple of miles away, so that we could look at longer timescale increases in more than 50 different VOC compounds and methane. We also, at those sites, deployed continuous VOC sensors. These were PID, or photoionization detection instruments that monitor at high time resolution changes in overall VOC levels. And when we detect elevated VOC plumes, those automatically trigger a canister which collects a sample that comes back to the lab to again give us this detailed speciation about the plume concentration and composition. Finally, we had mobile measurements of methane and VOCs, but I won't have time to talk about those today. So we're going to begin by talking a little bit about concentration increases around the well pads on both short and long time scales. Here we're relying on the weekly and the plume-triggered canister VOC concentrations to look at these spatial gradients. And remember, we have many different VOCs that we've measured this for. Here it's summarized for the different sites and for different operations, but even this is really too much to look at. So we're going to focus just in on one example, which is kind of typical of the patterns we saw. So this is well pad number 2 in our study, which was undergoing drilling operations. And in each of these panels, we're looking at the concentration distributions around the well pad for different hydrocarbon groups. So for example, in this top panel, on the left side of the red dashed line, we're looking at the weekly integrated canister concentration distributions. And the distribution to the right, closest to that red dashed line, is for our background site. And then the other 2 are some of our near pad monitoring. So we see, for example, here during the period of drilling, this increase in these C8 to C10 N alkanes. So this is octane, nonane, and decane. We've done quite a bit of work in this project looking at the source of these compounds, and these are closely associated with the use of a synthetic drilling fluid to make up the drilling mud. This is enriched in some of these longer N alkanes, and we find them emitted both in the lab and out in the field at significant amounts from the use of this particular Shell NeoFlow product. This is increasingly popular in the DJ Basin because of its lower odor impact compared to traditional drilling muds. If we look at these compounds, or for example, BTEX, we find that the concentration increases are observable near the pad on weekly timescales, but they're not particularly dramatic. We see much bigger increases if we look at these more transient plumes. And most of these plumes that we detect persist at our monitors for less than an hour, but they have concentrations that are typically a factor of 10 to 100 higher than we see, for example, in the average concentrations in this region. So we can take all of this kind of data and focus in on some of the hazardous air pollutants and assess some of the potential risk associated with exposures both on short and long time scales. So here we've summarized this data for the study for our 3 different monitoring sites. And we've included here examples for benzene and nonane, which is coming from this synthetic drilling mud. And what we're plotting here are distributions of hazard quotients. The hazard quotient is simply the measured concentration divided by the corresponding health guideline value. So for example, for chronic exposure, which is shown in these green distributions, we're looking at the chronic health guideline value for benzene or nonane, and we're comparing that to the measured concentrations. So a value of 1 means the measured concentration is at the health guideline value. And fortunately, what we see here for all of the sites in terms of the chronic exposure, the green distributions, these fall well below this value of 1. So the measured concentrations are typically well below those health guideline values for long-term exposure. One thing that is interesting is that normally this sort of risk assessment is dominated by benzene, but during drilling operations, we find contributions almost as high from nonane, from these synthetic drilling fluids, as we do from benzene. But again, both of them are well below the health guideline value for long-term exposure. If you look at the yellow and the blue distributions, these are for short-term or acute exposure. And here we're looking at hourly concentrations compared to acute health guideline values. And we'll focus here just on benzene. We find that most of the time those hourly values are below, but we do see some hours at site 1 and at site 3 where we have measured concentrations above those acute health guideline values. So distance is, of course, an important factor here. And at sites 1 and 2, for example, most of our monitors were between about 1,100 and 1,400 feet away from the operation. Colorado has a presumptive setback distance of 2,000 feet, although there are sometimes exceptions to that. So what we did was use the EPA regulatory dispersion model, AirMod, constrained by our observations in these black dots, to predict what we expected concentrations to look like during these individual hours of elevated concentrations as a function of distance. And you can see, fortunately, at 2,000 feet, we generally expect concentrations in our observed situations to be below the acute health guideline value for benzene. But of course, not all areas of the country have a 2,000-foot setback distance, and particularly as you move in closer to the well pads, it's expected that you would see an increasing frequency of concentrations above this health guideline value. So the other thing that I want to touch on before I wrap up is some of the work we've been doing to develop part of this TRACER emissions model. And our focus, not surprisingly, is really on characterizing the situation during pre-production. As Leah mentioned, we'll have a more detailed discussion about the modeling efforts in the second webinar on February 13th. But the idea here is that stakeholders could have a user-friendly model that would allow them to define an operational timeline, select from relevant emission factors, and predict emissions timelines, and using dispersion modeling tools, translate those into potential exposure as represented by concentration timelines. And one of the key things here is to have relevant emission factors that correspond to current operational practices. So the final thing that I'll show you is just a little bit about some work that we've been doing, trying to update emission factors for current practices as we see them, for example, in the Denver-Julesburg Basin. So what we did here was we used extensive VOC observations from quite a few sites in a separate study that was going on in parallel in Broomfield, Colorado, during the development of 6 large well pads. And we basically used the dispersion model tool as a way to invert those concentration measurements to constrain emission rates at different pads for different operations as they were going on. And some of the things that we found, for example, we now have updated estimates for drilling mud volatilization. As you remove drilling rig combustion sources when you electrify, you tend to be dominated by emissions from drilling mud volatilization and entrained hydrocarbons. So we have now modern estimates for that, including this increasingly popular NeoFlow-based drilling mud. We have the first VOC emission estimates for an operation known as coiled tubing or mill out. This is the stage following hydraulic fracturing when the pressurization has been done in isolated stages, and they go in and they mill out those plugs that separate those stages. And there's significant venting of VOCs to the atmosphere. So we find that to be important. And then finally, as I mentioned earlier, we find in these particular cases where they were using closed loop tankless systems for fluid handling during flowback, we see reductions in emissions of more than 95% in terms of total VOCs measured and in terms of this critical HAP benzene relative to what we saw even a few years ago with other green completion techniques. So let me wrap up with just a few key reminders of points. We do see increased VOC concentrations around well pads during both pre-production and early production operations. But it's really the transient plumes that have the high concentrations relative to what we see in the regional background. And therefore, as predicted in a previous Colorado-sponsored health risk analysis, we find that the greatest non-cancer health risk is likely associated with short-term exposures. So we need to monitor those well. Secondly, the use of grid-powered electrified drill rigs definitely reduces NOx emissions and also some VOC emissions, but we still see substantial emissions associated with outgassing from drilling mud and entrained hydrocarbons during drilling mud recycling operations on the pad. And then finally, as I just mentioned, the implementation of some cases of closed loop tankless flowback systems really helps to substantially reduce VOC emissions on average during flowback. We previously saw this as the biggest source, but this technology is helping to reduce that. However, we do still see some large emission pulses over shorter periods that seem to be associated with emptying of sand canisters that trap sand coming back up out of the well during flowback. So I will stop there and turn things back over to Ted.
Thanks so much, Jeff. And your last speaker today is actually me. So let me bring up my presentation and we can go from there. So I will ask, do you all see it?
Yes, we do.
Wonderful. So what I'm going to talk about today is just a glimpse of the results from a NASA HAQAST Tiger team investigation, and I'll go into that program, etc. And first, I'd like to acknowledge my co-authors, both at Georgia Tech, as well as Dan Goldberg at GW. So with that, a number of people have contributed. This was largely funded by NASA and the NASA HAQAST program, which I'll talk about in a second, but really motivated by work being done that you've just heard about. Actually, that was the real driver. So here's the outline, and we'll go through that just a matter of time. You can get the slides so you can see this in more detail if you wish. So just as a little bit of background before going into this, the NASA HAQAST program was put together to really do some applied science to use Earth system products. And by that, most notably, people use satellite observations, but it includes aircraft observations, air quality models, et cetera, to look at health and air quality concerns. The NASA HAQAST program has a Tiger Team effort where we put together teams from multiple universities to address specific problems over short timelines. And so if you're not familiar with HAQAST, I just recommend going to their website because I really can't do it justice in this short time. But as part of that, we put together a Tiger Team amongst a number of us to address oil and gas developments on air quality and light at night. And that's what you're going to be hearing about in this, as I speak. So this is the UOGD Tiger Team, and you can see the range of types of activities we had planned to do. So specifically, our objectives were to get a better idea of the spatial footprint of UOGD operations on air quality using satellites and models in this case, and not only of direct emissions, but also of secondary products, and to look really at a larger scale, more regionally than the measurements that you just heard about. And so the potential outcomes we were looking to, we're really looking at the spatial footprints and trends because we can use the satellite data over multiple years to look at how those concentrations are changing over time. So our approach was to use the CMAQ air quality model to link oil and gas operations to air quality impacts around the U.S., not just in the TRACER study regions, but really across the United States, and look at species that have been talked about already, such as ozone and formaldehyde and benzene, but look at some other species as well, most notably PM2.5. And as part of that, we're comparing our observations with air quality, both the TRACER observations as well as the more routine observations. As part of that, we compare our results with the satellite vertical column densities. And I'll tell you, so a vertical column density, it's not a concentration, it's the number of molecules in a column of air going up to space. So you don't get a concentration directly, but we do model VCDs. And so we can compare the model to the satellite observations as well as ground level concentrations. We are using two different satellites, particularly Tropomi and Tempo. And they have, Tropomi has been a more long-term, Tempo is a new one that's really exciting. And then we're using those observations to look at trends. So the areas modeled are the ones that are in yellow, red rectangles across the U.S., covering a number of plays. We simulated June 2023 to August 2024, actually a little bit longer than that, really to coincide with the TRACER studies. Results are available if you want them. As part of this, CMAQ has this utility that's called ISAM, the Integrated Source Apportionment Model, that allows us to sort of hone in on specific impacts of specific emissions. In this case, we're looking at air quality impacts from specific plays across the US. So just to give you an idea of what sort of emissions they are, just looking at this, are the NOx emissions from the various plays that we're using in the modeling. Really, this just shows you that places like the Permian have some of the highest, most dense emissions, but you can see sort of the distribution is across the US. When we apply CMAQ, this is the results we get at the broad scale. So this is not UOGD specific, but you can just see what the concentrations predicted of a number of key species across the US are, in this case, showing formaldehyde as well as ozone. One thing I might note is that if you look at the plot on your left, is you get very high formaldehyde due to biogenic regions, and so that's what you would be seeing over like Alabama and such, but also we see them over some of the oil and gas development regions. So let's hone in and look at some of the oil and gas specific impacts and using ISAM and such. So first, looking at ozone, we've heard about that. And if we look at the grid maximum ozone as modeled in 2020, the summer of 2023, you see the distribution on your left, and this is specifically due to oil and gas operations. And what you see, you can very much see the Permian, Eagle Ford, Bakken impacts, but you see there's ozone impacts across in other plays as well, and that they're much more regionally distributed. If you look at the average, you can see very much this regional impact on ozone. The largest impacts, the grid maximum at any time during the summer would go up to about 35 ppb, but then that drops off as you go away. If you start looking at the average over the season, it's more on the order of 16 ppb. And this is very comparable to what you saw from the TRACER teams in terms of some of the elevated levels at some of the different sites, particularly in the Permian. We also have results for other pollutants from oil and gas operations. And here what I'm showing are for formaldehyde, benzene, and toluene. And of interest, if you look at the benzene, this is the average annual, we get about the maximum is about 1.5 ppb in the Permian. Typically it's rather less, but if you recall from Meredith's talk, this is right in line with what they are finding. And in terms of formaldehyde, you might get up to a couple of ppb for the annual average, typically with highest levels of about 6 ppb in any location. So we've got these for other air toxics as well, whatever CMAQ simulates. So we have this range, but what I think this really shows you is the footprint of both the air toxics impacts as well as the ozone impacts. We've also compared our results with Tropomi, which is one of the satellites, and between CMAQ and Tropomi. And one reason you do this is to see how well you're capturing the emissions. And in particular, we're comparing what we have. We've simulated for NO2 VCDs with the observed NO2 VCDs. And you see on your right that the top graph is CMAQ, the second plot is Tropomi, and you see that they compare quite well. But there's some interesting results when you look at the difference. And you see that in some basins, maybe the Uinta and such, there's a bias high in the modeling, which would indicate that our modeled emissions are high. And in some areas, the Permian and the DJ basin, the model seems to be somewhat biased somewhat low. So one of the things that this does show is this comparison. It helps us identify potential areas of concern in terms of how well we're capturing the emissions. When we look at the Tropomi trend analysis, this is work really being spearheaded by Dan Goldberg. What he did is he used Tropomi over multiple years and looked at the spatial distribution of NO2 as well as other pollutants. We'll see that in a second, over time, and of the different basins and of the different cities. And he's got those circled. The black areas are urban, the red are oil and gas operations. So using Tropomi, he looked, before we go on, just to give you an idea of the level of detail you can get from this sort of analysis, this is the Tropomi NO2, formaldehyde, and CH4 over the Permian Basin. And so you see these, you can do a comparison between the different satellite retrievals, and we can also compare that to our model results. And so if you recall from an earlier slide, I had the formaldehyde, and what this shows is the, let me actually get the pointer, how well the model is capturing the space observed observations. So there's this real correspondence. But what Dan did that's really neat is he looked at this and he was able to do a trend analysis. He looked at the observations differences between 2023 and 2019, and he shows that there's increasing levels of NO2 in some of the basins, such as the Permian and such. There's actually a decrease in most of the cities. You note here, Denver, Los Angeles, NO2 is going down, whereas in some of these plays, the NO2 is going up, though maybe not the Bakken. So one of the things this can be used for is not only comparing how well the modeling captures these levels at present, but also doing a trend analysis and seeing how that compares with activities that are observed. So if you look at the oil and gas areas, they tend to be getting higher with time, except for the Bakken. And this very much aligns with what Leah showed at first, that talked about the activity. So just as a summary, talked about what the NASA Tiger team is up to, just giving you a glimpse of what we have. And if you have a desire to sort of get some of these results, we're quite open to that. And we are continuing to use them to better understand oil and gas operations. I think overall, combining the modeling and the satellite analyses really shows how they can work together, and we plan to continue this analysis into the future over the next year. My last thought is go to the HAQAST website for additional information, not just on this work, but on a range of other interesting studies that's being done, linking satellite observations with observations at the ground level and earth science models. So with that, thank you very much. And I think it's time to open it up to discussion. So with that, Coel, do you want to take over and lead the discussion period? Well, I'll lead the discussion period, but just open it up.
Yeah, so if you have any extra, I see that people have been putting questions in the Q&A. I can read a couple that haven't been answered. And then we've got a couple topics to discuss among the team. One of the questions that came up in the Q&A are those downward nitrous oxide NO2 trends in the Ohio River Valley a EGU signature?
Without a doubt, it is. That we're capturing the emissions going down from the power plants as well as within the cities. That's something that there's been longer term trend analysis, and it's very, very clear using the satellite data. And I also see why is there ozone seen in Lake Michigan? That's actually quite interesting. It's actually observed. And why it is because ozone does not deposit quickly to water. And also the the mixture of air from the cities gets over the lakes and essentially is allowed to cook. There's often a lower boundary layer, so it's trapped closer to the water. And so you do get elevated levels of ozone over bodies of water, not just Lake Michigan. If we went back, you'd also see it's over the coast over the ocean near the coast. It's just because the meteorology and the lack of deposition really enhance ozone formation.
There's also a question about any NO2 trend analyses done for Canada.
So that's been done. That's not off the top of my head to give you. But you can look at some of the work. I think that by Dan and some others. So they're using the satellites to look pretty much over the globe.
Folks who got their questions answered in the chat box, if you have further or follow on, please don't hesitate to pop them in there. I have a couple questions just for general discussion. I don't know, Meredith, if you want to come off of mute or come back on video. Can you talk about a little bit of the, what might be the cause of the differences between what you saw in the Permian and in Colorado or Eagle Ford? And this is for Leah, Jeff, Meredith, anybody who wants to kick that off.
Maybe I can start there. We've also done some work down in the Permian prior to this with the National Park Service looking at Carlsbad Caverns. There are some big differences in operations, the kind of flaring that you see, for example, in the Permian. When you look out from Carlsbad Caverns National Park, you see what looks kind of like a city out there, all of the flares. And that's not so common in the DJ Basin. We do have enclosed combustors that are used, but we don't have the sort of open flaring as much. I think another thing that's important to keep in mind is the proximity to the source also has a big influence on the concentration. And I showed a little bit about how, things disperse and dilute as you move further away from the source. So, Meredith, for example, showed concentrations at their stationary site that were generally higher than in the DJ Basin. But if you look at some of our near pad measurements in the DJ, they're higher than what they saw in Loving. So some of these differences have to do with operational differences. Some have to do with just how much dilution has happened between the point of emission and the location of the measurement. So we need a lot of context to really interpret some of the differences.
Meredith, did you want to add to that?
I might just add that another potential reason for differences is the fuel composition. So the higher sulfur content that we saw in the Permian.
And Meredith? Okay. I'll put this to the panel. How do you think this research can be used by decision makers across the broad range of types of activities?
So perhaps one thing is just thinking about setback distances, and I know this is an active discussion in some basins now. Having information about emissions and how they impact air quality at different distances is, of course, key to informing that decision. So some of the results here definitely provide new information in that regard with respect to HAPS exposure.
If I may.
Other thought, yeah.
Yeah, I'd
Gunnar.
like to extend on that and saying that it's not just the distance, and so the setback is a measure that may help, but if you're pretty far from a particular source, so in other words, you're way below that setback distance, but you live in an area that within 10 kilometers or more has a lot of wells, you may actually be much more exposed as compared to having just one site that's right next to you. So the setback policy as such is a poor measure that actually does not address the overall exposure. I think that's one of the takeaway points.
And Gunnar, do you want to just give us a 30-second biography? Just who you're with and such?
Yeah, Gunnar Shah at Texas A&M University. I was in charge of the passive sampling networks in the Permian and the Eagle Ford. And one of the outcomes from that is that actually jibes very well with some of the modeling work in Leah's group, is that it is not so much important what is right next to you in terms of the overall average concentration and its variability. It's the whole picture that is important. So if there are a lot of wells, if you live in an area where the well density is high, even if you're not very close to any of these wells, your exposure may still be quite significant. And this, for example, manifests itself in the highest exposure in the Eagle Ford on the northern end of the shale, because there's a much longer fetch that the emissions accumulate into. So under typical southerly winds, there's a lot of wells that are upwind of you, while if you live in the southern part of the shale, there is many fewer wells upwind of you. And even though there's same amount of wells maybe in your near vicinity, your exposure is going to be much higher if that fetch of emitters is much longer.
Yeah, and thanks, Gunnar. And he's part of Meredith Franklin's research team.
Yeah, I just wanted to follow up, Ted, that Gunnar's absolutely right in terms of long-term exposure, but in terms of short-term exposure, there you really are dominated by proximity to high emissions close by. So we need to be a little careful not to mix these things together because they're quite different. So chronic exposure certainly depends a lot on the total emissions, but we see a lot of the risk associated more with these short-term exposures, which are driven a lot by proximity to sometimes short-term emissions associated with specific activities.
We have a question in the chat that I'll just read off real quickly. Did you observe emission differences between age of well pad, age of flare stack, and size of operator?
Can Leah, Jeff?
I guess I'll just jump in at that we did not select wells for their size or age. And so we, we've kind of focused when we were driving around the wells, we were focusing on measuring emissions from flaring, and we have gathered the information about kind of the flaring volume, the volume of gas fed to that flare on sort of like an annual basis. They were all relatively small flares compared to, let's say, industrial flares, right? And so we did not, that was not kind of part of our project or our scope to really look at different ages. And I had responded to this in written text to one of these, the other questions was about the, sorry, I lost my train of thought. But the main point is that the other question was about whether the flares were up during pre-production or during production. So we measured everything in production. In that sense, they're, so mature wells, but we don't have information on sort of, 5 versus 10-year-old wells.
Yeah, and our study was all focused on newly developed wells or wells being drilled and completed or into the first few months of production.
So we got another question for the panel is what sort of follow-on work do you think would be best to tease apart the variations in exposure? Basically, where would you go next?
So for pre-production emissions, we still know relatively little about exposure associated with those. And, we've done now a couple of studies in the DJ Basin, and we've seen big changes in emissions and impacts as operational practices have changed. For example, the closed loop fluid handling systems I mentioned has made a huge difference on pads where that's implemented. We don't have much of that kind of information in other basins around the country, really looking at detail at operation-specific emissions during drilling and completion. So I think, better understanding the operational details in other basins would be helpful, and making measurements in other basins of pre-production exposures would also be really useful.
And I guess I'll just add to that is that doing the modeling in all of these basins would also be useful. So I talked in these measurements slide about differences in the measurements in the Eagle Ford and the Permian, but we haven't actually, as part of this collaboration, we haven't done the modeling in the Permian. So one interesting point would be, does the model see these differences as well? Can we predict these differences based on what we know about the emissions?
Ted, I'm just gonna jump in. There's a couple more questions popping up in the Q&A, and I'll just take it from the top real quick. There's one for those of you who did some work in Texas. Did you do any comparison between TCEQ data and yours?
Yeah, so we have some comparison, and there's not a perfect overlap in instrumentation and measurement capabilities, but we have some comparison between like the GC hydrocarbon measurements from the TCEQ and then hydrocarbon measurements from our WOCUS PTRMS instruments. And I mean, the quick answer is they agree really well. We've also both had some NOx and ozone measurements that were temporarily co-located. So we did do those co-location studies with TCEQ data where we could.
Yeah, same thing here. In our case, one of our passive samplers was about 1 kilometer from the TCEQ site, but was more central to town. So interestingly, it showed some very good comparisons with the monitors and others where there were differences.
Just a follow on, Gunnar, there's a question specifically for you. Have there been any studies of emissions in high density in terms of number of wells, but not in a highly dispersed area versus, I think this is a question about density of wells versus concentration that might be measured at a particular location.
Yeah, so our network sites in the Permian had various numbers of wells surrounding them, and that changes depending on the buffer size that you count. We have counted relatively small buffer sizes, and we do see a correlation between well numbers in the buffer and the average hydrocarbon level at the site. But I haven't so far not analyzed this in terms of a very specific distance pattern, if I understood that question correctly, right? So my guess is that probably our measurements are not good enough, so to say, to tease out very small differences like this.
So if I understand the question correctly, I might offer it that I think some of that can be answered with the modeling capability we have now. So if we wanted to look at impacts of well density versus the sort of emission factors versus how strong dispersion is, those kinds of experiments can be run in the model, and that's one of the reasons we have a model.
Stay tuned. I think we have time for one last question. There's one last question in the chat. The question is, are there particular pollutants of concern for the chronic exposure scenario that we've been talking about?
I think that goes to Jeff.
Yeah, so benzene tends to dominate the risk just because it's potent as a hazardous air pollutant. The health guideline value for chronic exposure to benzene is much lower than for most other VOC HAPs. And there are many sources of benzene in the oil and gas sector, as well as other things like traffic as well. So we tend to see that approaching the health guideline values more quickly than others. We did see no-name during drilling operations pop up with some interest there, but usually benzene is the sort of the number one focus in terms of risk.
I can maybe just follow up on this. With the VOCUS, we saw hundreds, more than 1,000 of different compounds. And some of them are, for example, oxygenated that have not been measured by the GC earlier. And a lot of those compounds that we are now able to observe, they don't have any toxicity studies at all. So benzene is a no-brainer. It has very very high toxicity. And so even at low concentrations, it's quite toxic. But there are a lot of other compounds and secondary products that get produced in photooxidation and so
on. We are at time, so I am just going to wrap up very quickly with a thank you, a hearty thank you for all of our attendees and for our speakers and panelists. Thank you so much for attending our webinar. This will be available on the website in the next coming weeks. And if you want to continue to follow our activities related to this project, you can sign up for updates at the energy program at the link listed here. We've got a few things coming up. So the next part of this series is on February 13th, and I believe that that link will come out with a follow-up email if it's not in the chat already. In this webinar, we'll talk a lot more about modeling. We've got a few community open houses that will be taking place in the TRACER locations. One will be virtual. And again, more information will be coming. In May, there will be a website with all of these data. HEI has our annual conference also in May, and we'll have a full session dedicated to this work. And the final reports for each of these studies and more will be coming over the next year. So in the meanwhile, please stay up to date with this work at our website. Thank you again. And we'll send all this information out with a follow-up email, and again with a survey on this webinar. We hope to get some feedback on. So for more information, you can check each of these research groups' websites, which are listed here, and we'll share them. And with that, thank you so much.